Everybody, in this video, I'm going to go through our lesson on rotations. So this kind of goes hand in hand with our lesson on transformations. All right, so let's talk about what rotations are. So rotations turn your figure either clockwise, which means like the hands on a turn clock, on like the hands on a clock turn, or counterclockwise, which means opposite of the way the hands on a clock turn. So it'll either turn your figure clockwise or counterclockwise. And your figure is going to turn around some fixed point. Which is called a center of rotation. Really, it'd be the center of rotation. So the center of rotation, this can be anything. It could be the origin. It could be a vertex in the shape. It could be any point. Think of it as this is the point that it is spinning around. I like to think of it if it's like a vertex on your shape, you're holding the shape down at that vertex and you're spinning it around. Okay. So they turn around a fixed point called the center of rotation. Your figure also turns a specific measure of degrees called your angle of rotation. That's right, the angle of rotation. So in general, we have kind of like, 90 degrees, 180 degrees, 270 degrees. So let's talk about what those look like. So if your point spins, ooh, that was my cat that just sneezed. If it spins 90 degrees, it is essentially going a quarter of a circle. So 90 degrees is a quarter of a circle, or you could even think of it as, I don't know why I wrote out quarter, it's 1/4 of a circle. That's 90 degrees. 180 degrees then is 2/4. So if your point spins 180 degrees, it has spun 2/4 or half of a circle. And this is the same whether you go clockwise or counterclockwise. You're going to end up at the same spot. 90 degrees clockwise versus 90 degrees counterclockwise, those are different directions. You're only going to go a quarter of a circle, but a half of a circle either direction, you're going to end up at the same spot. Next we have 270 degrees, which is going to be 3/4 of a circle. So your point would spin all the way down here. I'm gonna form this quarter circle shape. So 270 degrees is 3/4 of a circle. So you're just missing that last quarter. So if it spins then all the way around, that would be 360 degrees. All right. So, and I should just include that in here because it's important to note that if you spin all the way around a circle, that is 360 degrees. Say full circle. In the center here to be the center in all of our rotations. So 90 degrees, 180 degrees, and it's been down 270 degrees, and it can spin all the way back up. All right. So an important concept that we kind of need to define here is something called, and we've talked about this before, a line of symmetry. And your line of symmetry, that's really a line that can be drawn through a shape or a figure. So one side is a reflection of the other. So if we have, for example, just perhaps a triangle. We have some different lines of symmetry here. So I could draw this line of symmetry. And if the shape flipped over that line of symmetry, it would be the same. It's a mirror image on either side. And I could do that through this point as well. And through this one. These are our lines of symmetry. An important idea here, because when we're talking about rotations, we oftentimes hear about something called the rotational symmetry of a figure. So what is rotational symmetry then? And rotational symmetry is when an object or a figure is rotated around its center and it's got to be less than a full turn. And the rotated figure is the same as the original. So when a figure is rotated around its center and the rotated figure is the same as the original. So I'm gonna draw kind of a different shape for this one. Let's do a square. I don't know why I made it. There you go. So if I take this square, how many times or how many degrees could I rotate this shape to where it's going to rotate and be the same exact shape that it is right now? So think about, if we take this one side, we could rotate this one side 90 degrees. And if we rotate it another 90 degrees, we would end up at the same shape. If we rotate it another 90 degrees, we would end up at the same shape. And if we rotate it another 90 degrees. So when it's rotated around its circle less than a full turn, which means less than 360 degrees, and it's the same as the original, that shape has rotational symmetry. So this is a 90-degree angle of rotation that maps, the original shape onto itself. Think about turning the square 90 degrees each time. Whichever way, either way, doesn't matter. So, and this is for way later. I didn't scroll it down or bring it down at all. An important note here is that regular polygons have rotational symmetry. So regular polygons have rotational symmetry. So what does that mean? Well, please remember, oops, I already flipped it over, that in a regular polygon, all sides and all angles are congruent. So when we have these sides that are all the same, your regular polygon is going to have n number of sides. So with that number of sides, you can then use that to find your angle of rotation. And really, the number of sides that that shape has, you divide that by 360. So how many times can that side really turn on itself? So that would be 360 degrees divided by n, or the number of sides. And oftentimes your angle of rotation, that's m, because it's a measure. So for example, here, if we have a pentagon with 5 sides, that means n is 5. Then we can find this angle of rotation, or m, by taking 360 degrees and dividing it by our number of sides, which is 5 sides. And 360 divided by 5 is 72 degrees. So if we take a pentagon and we rotate it around its center 72 degrees, the pentagon's going to be the same. It's going to be the same shape. All right. Next thing, or kind of last thing I want to take notes on before we look at 2 quick examples, is rotations about the origin. So that means kind of like in the coordinate plane. Oh, I wanted to make a box, but that's okay. So we're going to kind of set up a coordinate plane for this. Here's my y-axis, and here's my x. And 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Kind of just a rough drawing here, not really to scale. And we'll work with the point 3, 1. So that's going to be our point here. And what happens in general if we rotate about the origin 90 degrees clockwise? And again, this is about the origin. That's the key here. It's around any other point. This does not work. Your point x, y is going to become the point y, comma, negative x. And let's think about y. So we're taking this point 3, comma 1, and we're going to rotate it 90 degrees clockwise. So it's going to go a quarter of a circle down basically one quadrant. So that would be where our previous y value, right? We had x was 3 and y was 1. Now this new point, oops, I did it wrong. We'll go down here. It looked wrong when I drew it, so that made me feel better. We have this new point 1, comma, negative 3. You flip-flop them, right? X and Y switch. And then that X becomes negative because it has gone clockwise 90 degrees. So what if we go the opposite direction? What if we rotate 90 degrees counter clockwise? So if we take this point 3, comma 1, and it goes 90 degrees in the opposite direction, now it is going to be the point negative 1, comma 3. So this x, comma y is now negative y, comma x, right? The x and the y switch places, but now this time the y value, which is now the new x, it became negative. So flip them and then make that first coordinate negative. Now, this one's my favorite. What if we are going to rotate 180 degrees? And really, this is either direction. Because notice whether I follow the 90 degrees counterclockwise path or the 90 degrees clockwise path, if I rotate it 90 degrees one more time either way, I'm going to end up at the same spot. So if we rotate 180 degrees either direction, your point x, comma y is now going to be the point negative y, oh sorry, nope, negative x, negative y. I was looking at the example above. So think about it. If we rotate another 90 degrees clockwise from where we are at negative 1, 3, we would rotate it again. Oop, 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 oop. And now it's going to be at the point negative 3, negative 1. Or if I rotate it 90 degrees clockwise from where we had already rotated 90 degrees clockwise to, right? If we're working from the point 1, negative 3, and we rotate it 90 degrees clockwise, we're going to end up at the same spot. So this is the point negative 3, negative 1. All right, let's look at some examples. We're going to be 2 quick examples here. Oh, this image. It's always hard to predict how much space. Number 1, what is the smallest degree of rotation that will map a regular 16-gon onto itself? So one key here is that this is a regular polygon, and this polygon that is regular has 16 sides, which means that n is 16. And please remember our angle of rotation formula is equal to 360 degrees divided by the number of sides we have. So our angle of rotation M is 360 degrees divided by N, which is 16. So 360 degrees divided by 16 sides, because really it would just rotate on each side. So 360 divided by 16 actually gets you 22.5 degrees. So that's the smallest possible number of degrees we could turn a regular 16 gon, and it would be the same shape. All right, now we're going to use this drawing. But first I want to write a little bit of text. So triangle IJK and triangle DEK are shown. Describe two rotations that will map triangle IJK onto triangle DEK. And then of course we have the images. Make this a little bit bigger. And these are in the OMHS. Either you could recreate this just by hand or print it out if you have the means. But we are going to start with IJK, and we want to rotate IJK so that it maps onto DEK. And we want to do this actually in two different ways. So method A, I could take this IJK and I could rotate it around. It looks like it's going to be rotating around this fixed point K. And we could rotate it counterclockwise. So I could rotate triangle IJK counterclockwise about point K. So about K until these slopes are equal. So until the slope, for example, of IJ is the same as the slope of DE, because that means then that these are in the exact same position. So we'll rotate IJK counterclockwise about K until corresponding segments have the same slope. Or until point J is on top of point E. But we don't necessarily have that drawing for reference. How do we turn IJK into that without even knowing DK is there? So that's one way. And then we could also go the opposite way, right? I could also rotate triangle IJK clockwise about K until these corresponding points or corresponding sides have the same slope. Corresponding sides have the same slope. So you can always rotate it, you know, clockwise or counterclockwise. Oh, I just motioned the wrong way, but that's okay. Please let me know what questions you have about rotations, and I look forward to seeing you in class.